Alright, so in this video we're going to talk about the definite integral and the fundamental theorem of calculus. So we'll start with the definition of the definite integral. So the definite integral is the limit of the Riemann sum as n goes to infinity. This provided this limit exists. Okay, so let me remind you the Riemann sum. So the Riemann sum looks like this. It's the sum from 1 to n of f of a plus b minus a over n times I, all times b minus a over n. And you should think of this as representing the sum of a bunch of rectangle areas. So we have some function f of x, we have an a, we have a b, and we want to find the area under f of x from a to b. So we look at right endpoints and the sum of all those rectangle areas. And each of those rectangles has a base width of b minus a over n and a height given by this function output at the right endpoint. So this is the height and this is the base width. All right, so now what we're going to do is we're going to take these rectangles and we're going to take their number to infinity. Take the limit as n goes to infinity. And you can see two things happen. One, the number of rectangles goes to infinity, and two, the width of every one of those rectangles goes to 0. So if you draw a picture of what happens, you're going to have these infinitesimally thin rectangles, and you'll have an infinite number of them. And so if you take any one of these rectangles, you can't really see it, but its height we're going to call f of x, and its width we're going to call dx. It's infinitesimally thin, so it gets a differential name. And we give this, this limit some special notation. It's going to be the definite integral from a to b of f of x. And this f of x is the height of our rectangle, our really thin rectangle, and dx is the width. So the integral sign is like summing over the areas of these rectangles. So if we think of the Riemann sum as giving us an approximate area, the definite integral gives us the exact area. All right, let's do an example where we compute this limit. So let's find the exact area under f of x equals 2x from x equals 0 to x equals 1. All right, so we're going to be computing a definite integral here. We're going to be computing the integral from 0 to 1 of 2x dx. And by definition, this is going to be the limit as n goes to infinity of a Riemann sum. I goes from 1 to n. We're going to have f of a plus b minus a over n times I, all times b minus a over n. We know b and a. B is 1, a is 0. We know the function. The function is 2x. So we can replace this general notation for our specific information. So f of x is 2x, so we'll just replace this with 2 times this a plus b minus a over n times I. A is 0, and b minus a is 1, so this is 0 plus 1 over n times I. And then again, b minus a over n is 1 over n. So if we clean this up, we'll get 2 over n squared times I. Now let's expand this sum. Just rewriting this without sigma notation. So this will be 2 over n squared times 1 plus 2 over n squared times 2, and so on all the way to 2 over n squared times n. We could rewrite this as 2 over n squared times 1 plus 2 all the way up to n, factoring out that 2 over n squared. All right, so we want to compute this limit. So n is getting large, so 2 over n squared is getting small, but 1 plus 2 all the way up to n is getting larger. So it's unclear if this is going to 0 or 1 or infinity. It's not clear what's happening here. So we need to rewrite this in closed form. All right, so imagine we have a 1 block, a 2 block, a 3 block, and then all the way up to an n block. So we want to find the area of all these blocks, 1 plus 2 plus 3 all the way up to n. So what we can do is we can take this stair-step looking shape, we can copy it and place it on top. Okay, this is the same shape. And the dimensions of this rectangle that we formed are n by n plus 1. So the area of the set of steps, is n times n plus 1. So the area of one of them is going to be n times n plus 1 divided by 2. Okay, so the claim is that 1 plus 2 plus all the way up to n is n times n plus 1 over 2. Let's test this. Let's say we have 1 plus 2 plus 3 plus 4. Claim is this is going to be 4 times 4 plus 1 divided by 2, or 4 times 5 divided by 2, which is 10. And if you add up 1 plus 2 plus 3 plus 4, you should get 10. So now we can take this, rewrite this as n times n plus 1 divided by 2. And the 2's cancel here, and then we can rewrite this as n squared plus n all over n squared. And you may recall when we are computing limits to infinity, we divide by the highest power term. So let's divide every term here by n squared. We'll get 1 plus 1 over n all over 1. And as n goes to infinity, this goes to 0. So this area is 1. Let's draw a picture to illustrate what we just did. Okay, so we have this, this function, 2x, it's this line. We're integrating from 0 to 1, so we're adding up this area. We're trying to find this area. And the area is said to be 1. That makes sense because the height is 2 and the width is 1. And the area of a triangle is 1/2 base times height. So 1/2, 1 times 2, which is 1. All right, so now I'm going to show you a different way to do this. And this is called the fundamental theorem of calculus. Fundamental theorem of calculus. It says if f is a continuous function over some interval a to b, then the definite integral from a to b of this function is equal to f of b minus f of a, where big F, this big F of x, is any antiderivative of f of x. Okay, this is called the fundamental theorem. Let's use the fundamental theorem to do the problem we just did much more quickly. So we're going to revisit example 1. We're going to compute the integral from 0 to 1 of 2x dx. Okay, so the fundamental theorem says all I need to do is antiderive this 2x, antiderive f, and then I can put in b, I can put in a, and take the difference. So I just got to figure out what the antiderivative of 2x is. The antiderivative of 2x is x squared. And now I'm going to put in 1 and 0, I'm going to put in the b and the a and take the difference. We represent this with a vertical line and a 1 and a 0. So this is kind of an intermediate step to this, the conclusion of the fundamental theorem. So now we'll put 1 for x, we'll put 0 for x, and we'll take the difference, and we'll get 1 minus 0, which is just 1. All right, so this theorem is very powerful. It allows us to avoid having to take a limit of a Riemann sum. All we need to do is take an antiderivative and then put those numbers in, the endpoints in, and take the difference. Let's do another example. Let's find the area under x squared over the interval 0 to 2. And we're going to use the fundamental theorem of calculus, FTC. So again, we're going to set up the notation here. We're going to go from 0 to 2 of x squared. And then the fundamental theorem says I need to just antiderive this x squared. I'll get x cubed over 3, or 1/3 x cubed. I'm going to put my 2 and my 0 in, and I'm going to get 2 cubed over 3 minus 0 cubed over 3, which is just 8/3. So this area, this curved area under x squared from 0 to 2, this curved area right here is exactly 8/3. That's pretty cool. Let's do another example. So in this example, we're going to find the area from 1 to 2 under the curve e to the 0.5x. Let me draw a picture. Okay, so this is what the function looks like. And we're trying to find the area from 1 to 2. So we're trying to find this area. Okay, so let's use the fundamental theorem. So we need to first antiderive this e to the 0.5x. It's going to be e to the 0.5x over 0.5. You can use u substitution, or you can use a formula to get this. And then we're going to put in 2 and 1 and take the difference. So if we put 2 into this antiderivative, we'll get e to the 0.5 times 2 over 0.5. And if we put 1 in, we'll get e to the 0.5 times 1 all over 0.5. And just simplifying a little bit, we'll get e to the 1, or e over 0.5, minus e to the 0.5 over 0.5. Dividing by 0.5 is the same as multiplying by 2, so I could rewrite this as 2 times e minus e to the 1/2. And I like that a little better than the decimal form that I have above. If I put this in my calculator, I'll get approximately 2.139. And that seems about right. If we do a box of that height, 2.139, it seems like the area of that box is going to be the same as the area of that curved shape. All right, I hope you found this video